Hello. We're right smack in our discussion of optimization word problems. Currently we're more interested in absolute extrema. Let's go back to relative extrema. How do you find relative extrema? Well, first we find the critical numbers. So a critical number C is by definition a number in the domain, which satisfies any of the following two conditions. So making two bullet points, either f prime of c is equal to 0, so you have a horizontal tangent line at 0, or f prime of c does not exist. F is not differentiable at c. So either you have a vertical tangent line there, or a sharp turn, or f is just plain not continuous at c. So some critical numbers are useless, some critical numbers yield a relative extremum. So how do we determine what's happening at a critical number C? We can use the first derivative test. Let's illustrate that for this scenario. Suppose you have the three critical numbers A, B, and C. What you do, according to the first derivative test, is determine the sign of the first derivative, f prime. Suppose the signs of the derivatives in these four intervals are negative, positive, negative, and then negative. So therefore, before a, the function is decreasing, and then after a, the function increases, which means that you have a low point at a, and so therefore f has a relative minimum at the number a. Now, before b, the function is increasing, and because of the negative derivative, after b, the function decreases. So it means f has a relative maximum. I realize the usage of a is unfortunate with the article a, but anyway, I think you get what I mean. A relative maximum at b, and at the number c, the function is decreasing before c and then continues its descent after c. Because there's no change in standard derivative, there's no relative extremum at c. Of course, if it was plus plus around c, then the function is increasing before c, also afterwards. Again, no relative extremum. So f has no relative extremum at the number c. An alternative to the first derivative test is a so-called second derivative test, named because it uses the second derivative, and it's the second of our derivative tests. However, it deviates radically from the first derivative test because it can only be applied to a critical number c which is of the first type. Suppose f prime of c is equal to 0. Meaning, if c is a critical number of the second type, you cannot use the second derivative test. You would have to go use the first derivative test to figure out what is happening at the critical number c. So, okay, suppose f prime of c is equal to 0, and f double prime exists in an open interval in, all right, in an open interval containing c, which means that the second derivative can be evaluated not just at c, but in the immediate vicinity of the number c, on its left and on its right. All right, so now what? Two scenarios where we get a conclusion. Suppose these are, in these two illustrations, the points on the graph corresponding to c. F prime of c is 0, so you have a horizontal tangent line. And then what you do, how you use the second derivative, is you check the sign of the second derivative when evaluated at c. Is it positive or is it negative? Because if in the first illustration, if f double prime of c is positive, the graph of f is concave up at c and it's in its vicinity, then what you see from this visualization is a low point at c. So in this case, f has a relative minimum at the number c. In the second scenario, because the second derivative at c is negative, then the graph is concave down at c and consequently in its vicinity. So what you have is a high point. So therefore f has a relative maximum at the number c. Let's use this on the following example. Consider the following function. Let's say f of x is equal to, if only I could write it down, f of x is equal to negative 2x cubed plus 6x squared plus 3. So the task is to find the critical numbers and use the second derivative test to classify them. I ordinarily would write it down, but writing with a stylus for me is not the easiest thing in the world. F prime negative 6x squared plus 12x. There are no critical numbers for the second type because it can be evaluated everywhere. So now it's just a question of when this would be 0. Let's factor this into negative 6x with x minus 2. This is 0 when x is 0 or 2. So you only have these two critical numbers and they're of the first type. You have horizontal tangents. Now for the first derivative test, you would have to set up a table of signs, but we're using the second derivative. F double prime using this first derivative, don't forget that negative symbol, is negative 12x plus 12. And then all we gotta do here is evaluate the second derivative at 0 and also at the critical number 2. The corresponding values are 12 and negative 24. Sorry, that's negative 12. Negative 12. Positive and negative. F double prime at 0 is positive. Think of a graph which is concave up. Think of an upright U. It has a low point. Therefore, f has a relative minimum at 0. Now, f double prime of 2 is negative 12, negative, concave down. Imagine a U which opens downward. It has a high point. So therefore, f has a relative maximum at the number 2. So that, folks, is the second derivative test. Yay! In some situations, the second derivative test is easier to use. Not in all cases, but it does provide us an alternative, especially when f prime is a function with trigonometric expressions. You may have encountered such a situation where setting up a table of signs is not the easiest, but if you're going to use the second derivative test, all you got to do is do these evaluations of the critical numbers, and you just have to determine whether the result is positive or negative, as what we just did in this example. However, the second derivative test has limitations. As already mentioned, for critical numbers of the second type, you can't use this. Also, one case we have not considered is, what if f double prime of c is equal to 0? So what if f double prime of c is equal to 0? Then in this case, the second derivative test fails. What that means is that we're not supposed to draw any conclusion. A lot of people fall into the trap of assuming, oh, in this case, the second derivative test fails. Does that mean there is no relative extremum? Nope, do not make that conclusion because anything can still happen as illustrated by these three functions. Take f of x equal to x to the fourth power, g of x equal to negative x to the fourth power, and h of x equal to x to the third power. You can verify that all these three functions have the critical number 0. For example, if you take h of x, its derivative is 3x squared. So it does zero out when x is equal to 0. Now, if you go further ahead and evaluate the critical number, sorry, the second derivative at the critical number, you're going to get the following values for the second derivative, all 0. And I invite you to explore that. I have a limit on the number of minutes for my YouTube video, so I won't go into detail. So these are three functions where the second derivative test fails. As I said, should we conclude that, oh, there is therefore no relative extremum? Nope, you shouldn't do that, because if you look at the graph of f of x equal to x to the fourth power, the graph looks something like this. It's not a parabola, it's flatter at the origin. But as you can see, you actually have a relative minimum there. And g of x equal to negative x to the fourth would be the reflection of the preceding graph, and it therefore has a relative maximum here at this point where x is equal to 0. And as for h of x equal to x to the third power, it's a useless critical number. Alright, there's no relative extremum there. So three functions where the second derivative test fails, and yet they were able to illustrate all the three possibilities, there being a relative maximum or minimum or nothing happening at C, which means that if you fall into this situation where the second derivative test fails, do not make any conclusion unless you actually know how the graph looks like, but otherwise, go back and use the first derivative test instead. Yay!